he is using this eventual epsilon nestedness. These words are not in any other analysis books in the world, only in this one. So that's why I am a little bit disappointed. I'm not saying they are bad, but I mean, we are sort of derailing. If you like curd and say, for instance, chicken, if you mix both of them, you cannot taste either one. So he is talking so rigorous things, unnecessary. What I think is, most important thing is, so far analysis is not given any, not given due place, I guess. Not any place, I should say due place. Anyway, so let's go to eventual epsilon steadiness. Now you yourself can understand before reading the definition. He says let epsilon greater than 0 for sure. A sequence is said to be eventually epsilon steady if and only if the sequence an plus 1, because this is steady for some natural number n greater than or equal to 0. Let's see if I stand and gently pass. Again, no, because we have to read this stuff. So you have a sequence. Again, in the world, sequences begin always from A1. And this person says 0 to the 0 is also 1, or even that Dr. Diana was also a little bit upset about it. Anyway, so suppose you have anywhere he begins, doesn't matter. So this one, eventually epsilon steady means you are given a first epsilon greater than 0. Eventually epsilon steady means far away you have some capital N. And after that capital N, all the terms are, if you take, I used the wrong word, not all the terms, if you take any two terms after N, I wrote N, say you have a capital N, after that if you take any two terms, distance between them is at the most epsilon. That is the meaning of eventually epsilon steadiness. I'm not familiar with this. So you eventually means after some day it begins. That's what he says. If and only if the sequence for some natural number n greater than or equal to 0. In other words, the sequence A0, A1 of n is eventually epsilon is if and only if there exists n greater than or equal to such that. So this one is better. So that is the meaning. Eventually epsilon steady means you go somewhere after a certain point, in any 2 points are at a distance at the most epsilon. Then he says in the sequence A1, A2. Now here he begins from A0, here he begins from A1, doesn't matter because An is 1 over n. That is the sequence 1, 1 over 2, 1 over 3 and so on is not 0.1 steady, but is eventually 0.1 steady. If he says 0.1 steady, that means it should begin at the very beginning. But when he used the eventual, far away any two terms of the sequence 1 over 1, 1 over 2, 1 over 3, far away somewhere, say some capital N. Beyond capital N, any two terms are at a distance at the most epsilon. That's what it means. The sequence 10, 0, 0 is not epsilon steady because of the first term. Distance between first term and any other term is exactly 10, so it is not epsilon less than 10, it's not epsilon steady, but it's eventually epsilon steady for any epsilon greater than 0. He is asking why, because eventually after first term, distance between any two terms is exactly 0. So it is less than any epsilon. Now he says, now we can finally define the correct notion of what it means for a sequence of rationals to want to converge. Cauchy sequence, a sequence again beginning from 0 of rational numbers is said to be Cauchy if and only for every epsilon greater than 0 the sequence is eventually absolute. This is very important. I mean, when I write, I say a sequence A is epsilon nested. Let me use this thing to save the time. For all epsilon greater than 0, there exists an epsilon, n epsilon belongs to n, such that for each nm greater than n epsilon, absolute value of an minus am, that is distance now, less than epsilon. This is how I write the definition of Cauchy sequence. Same thing he is writing some, I guess redundant stuff is there, but the same meaning. Cauchy, a sequence of rational numbers is said to be a Cauchy sequence if and only for every. Here, for every rational, by the way, actual definition is for every real number epsilon greater than 0, the sequence is eventually absolute. In other words, the sequence is Cauchy if and only for every epsilon greater than 0. Then here, he said for every rational epsilon greater than 0, here he says for every epsilon greater than 0. I wonder why on earth. There is capital N greater than 0 such that dAj ak less than or equal to epsilon. You understand, no? Eventually, epsilon is steady means, even Cauchy means far away, after a certain point, any two terms are at the most at a distance of epsilon for any epsilon. That's why I wrote, given any epsilon greater than 0, you can find an integer depending on epsilon. That's why I write n epsilon, such that if you take any two integers greater than n epsilon, then an minus am less than epsilon. So when you write this way, the advantage is very easy to write. The sequence is not Cauchy. What's the meaning of not Cauchy by looking at this? From his definition, kind of difficult, no? Same thing I have written, but even writing words, ne? Now if you say, suppose you go to town hall someday, there was a real big, humongous gathering. Then you go home and your mother is asking, Puta, where have you been? Amma, I went to town hall. What was that? Oh, million people, big party. That's not the way to say. Mother, oh my gosh, it's a humongous party. So I mean, even your voice and express intonation, words, no? I mean, it should be given the due place. In maths, that is very important in mathematics. You have to express your feelings. No, here, feelings have no place at all. Anyway, Puta, can you tell me what is the meaning of a sequence xn is not Cauchy, an is not Cauchy? If you know it, can you say? It's very important for us. After chapter 6, we have to, actually, chapter 6, even chapter 5, exercises are very important. You should try your best. Exceptionally important. Yes, I'm asking you, Puta.
The definition or just the meaning?
Yeah, definition. Very important. So, yes.
There exists
Before you say the definition, I told you the sequence you have here I have no sequence A1, A2, A3, all the way is said to be Cauchy, but no matter what epsilon you choose, somewhere you can find an n epsilon. After n epsilon, any two terms of the sequence is at the most at a distance of at the most epsilon. So that's how you will have to understand, feel and say. But when you are writing, if you are you have to write in a very real logical way. So what is the definition? We should not take too much of time.
There exists an epsilon greater than 0, such that for all.
Very good, you said such that. Thank you.
For all n epsilon.
No, not n epsilon. No. Because you said there exists an epsilon greater than 0, such that. Then n epsilon doesn't come. There exists. You using epsilon even, let's go. There exists an epsilon greater than 0 such that. Let me take this out of here so that it is easy for. There exists n belongs to n such that for every n greater than n, because over there I wrote n epsilon because it depends on epsilon to show that. No, my wife is Mrs. Ramasinghe, some relation like that. No? We are Sri Lankans. Indians say they are Indians, like that. For epsilon greater than 0, there exists n belongs to n such that for each n greater than n, distance between them is at the most epsilon, right? Now you are saying a sequence A is said to be Cauchy. There exists epsilon greater than 0 such that up to that point you are very good.
For all n belongs to
N, set of all positive integers, or say plus whatever. But can you say that? When you are at home, you need to play with this thing. Now, what do you say? You have the sequence A1, A2, A3, it goes all the way to New York or Chicago. You say it is Cauchy if and only if, no matter what epsilon you choose, there is an integer. I wrote n epsilon to emphasize the fact that it may depend on n epsilon. So you took any epsilon, there is an integer here. You take any two terms after that integer, distance is at the most epsilon. So from here, without going there, what is the meaning of sequence is not Cauchy?
mean that after
No, you cannot say now after. Let's begin from the picture.
definition.
Just if without writing, just explain. Somebody is asking you, Malli. So what is the meaning of A? The sequence A is not Cauchy. You are going to say you have the sequence, then like here.
After
Not after. I mean, you are going to talk like this or going to talk like here. Which one you are doing?
shall I do definition?
Okay, give me the definition. There we said then there is epsilon greater than 0 such that for all n belongs to n,
comma, for every
Putawa.
For some m larger than n, a minus am is larger than epsilon.
As that or equal
Larger than or equal to
for a minute. So anyway, isn't it correct? Then what is not Cauchy? There is epsilon greater than 0 such that for each n belongs to n, you said comma, very good. There exists n greater than n such that absolute value of n minus am greater than or equal to epsilon. You have to be able to say it, otherwise you are not an analyst. To make an analyst, you have to feel like that. So that's why actually when I was taking lectures at Columbia, half of the lecture is in Sinhala. Because then only they get the feeling. So if you are mad at somebody, you cannot your friend, Mokada, Jacob. That's the way to express your feeling when you are not happy with the man, no? Alright, you now understand, no? Here he is not talking about that. When I write books, or if you look at mine, if I say something it is called kosher, then I have examples of kosher. Then I say the definition of not kosher, then I have examples of not kosher. That's how the students understand. Because everybody is not, I mean, some people, of course, there are some students I have come across, just by looking at the definition, they understand. I mean, they are called genius, no? We are ordinary people. But we are going to be expected to be genius, no? I mean, what is field medalist? So, four of you are candidates, not me. Now you understand, no? What I am saying here, Puta, is to understand the meaning of a sequence is Cauchy sequence. You have to understand a sequence is not Cauchy. Otherwise, say, there is a Yogno, I mean, some boy from China came to USA to study. He has learned how to say thanks. So, wherever he went, he said thanks. He ran into a, street type guy. He understood that this guy does not know English. Then, whatever he said, Chinese guy replied thanks. Then he used some filthy words. Again he said thanks. Then he gave him a slap. He said thanks. You cannot do like that. You have to know how to say thanks and no thanks. No? In a louder voice also. That's important. Anyway, remark 5.1.9. I am taking time, but to the contrary, these are important. What do you think, by the way? Am I wasting time or no? This is very important according to me. At present, the parameter epsilon is restricted to be positive rational. But there was one place where it was not, no? For every epsilon greater than 0, he said. We cannot take epsilon to be an arbitrary positive real number because the real numbers have not yet been constructed. Okay? However, once we do construct the real numbers, we shall say that above definition will not change if we require epsilon to be real instead of rational. Proportion 6.1.4. That's why I told you this is the actual meaning of a Cauchy sequence. For each epsilon greater than 0, direct distance belongs to such that for each n greater than n, comma, here is a comma, absolute value of n minus n less than epsilon, right? In other words, we will eventually prove that the sequence is eventually epsilon steady for every rational epsilon greater than 0, if and only if it is eventually epsilon steady for every real epsilon greater than 0. We will be proving it. Understand that statement, no? See proposition 6.1.4. This rather subtle distinction between a rational epsilon and a real epsilon turns out not to be very important in the long run, and the reader is advised not to pay too much attention as to what type of number epsilon should be. I mean, it is, of course, because he is on the way constructing, we are talking about it, otherwise it is redundant. Example 5.10. So consider the sequence 1.4, 1.41 and so on. Mentioned earlier, this sequence is already one is steady. If one discards one is steady, if one discards the first element 1.4, then the remaining sequence is 0.1 is steady. If you subtract 0.1, but distance between this one and this one is
0.04.
Oh,
0.004.
0.004. Okay. So it is correct. Which means that the original sequence was eventually 0.1 steady. Discarding the next term gives the 0.01 steady sequence, etc. You understand this thing, so let me not spend time on this since you can understand. The sequence A1 up to A1, A2, A3 defined by n is equal to 1 over n. The sequence is a Cauchy sequence. That's a good one in my way, in my point of view. We have to show that for every epsilon greater than 0, the sequence is eventually epsilon f steady. That's what he says. So, I mean, we have to show what I have written here. And before you prove, if you can feel it, that's very good, because if you write 1 over 1, 1 over 2, 1 over 3. If you go far away, say after some point, distance between, difference between any two terms in absolute value will be at the most epsilon, because they are so small. So that is the idea here. We have to show that for epsilon greater than 0, the sequence A1, A2 is eventual epsilon is steady. So let epsilon greater than 0 be arbitrary. That's a good statement. We now have to find a number capital N greater than or equal to 1 such that the sequence AN plus 1 is epsilon is steady. That's clear, no? That's what we need to do, we say. Let us see what this means. This means that dAj, AK less than or equal to epsilon for every AK greater than or equal to N. So if you take here, now you get somewhere here 1 over J, 1 over K, we want 1 over J minus 1 over K in absolute value less than or equal to epsilon. That's what we need. So we need capital N. After that you to take two numbers J and K. We need 1 over J minus 1 over K, absolute value of that less than or equal to epsilon. So we need this capital N. Now epsilon is given, no? Arbitrary positive number is given. So it's very good that he has written it. That's the way to start. Yeah. Now since Jk greater than or equal to N, we know that 1 over J, 1 over K, both are less than or equal to 1 over capital N. So that 1 over J minus 1 over K is less than or equal to 1 over N here. 1 over J minus 1 over K is less than or equal to 1 over N. For sure. Both of them are less than or equal to 1 over N. So in order to force 1 over J minus 1 over K to be less than or equal to epsilon, it would be sufficient for 1 over N to be less than epsilon. That's clear, no? So what he is saying is, if this is less than epsilon, so definitely it satisfies what we need. So all we need to do is choose an N such that 1 over N is less than epsilon. Or in other words, N is greater than 1 over epsilon. So our question is, can we choose an N greater than 1 over epsilon? If we can do that, then we are done. So, but this can be done thanks to proposition 4.4.1. I cannot remember now what is this proposition because you cannot. It's not a good thing. I mean, say you are writing a geometry book for grade 6 students. You say Pythagorean theorem, you put a number. Instead of saying Pythagorean theorem, you say theorem 1.2.1. Then everybody wonders what on earth this one is. So anyway, let's see, 4.1, he has proved that over there, in particular, there exists a natural number n such that n greater than x. If you are given any rational number, he has proved that there is an integer n greater than x. That is a very important one. Actually, this is called Archimedean property. So still he has not used that word due to some reasons. Because Archimedean properties, that's a very, very important one. Very, very important one. What it says is, if you have given any real number, you can always find an integer n greater than x. So that is called Archimedean property. Like Archimedes. Archimedean. You will get it. I mean, today or I don't know, next day. So that's the proof. I mean, when he writes proof like this again, it doesn't come to your head. Let's write the proof. Now we need this. So you want to prove that? Theorem or proposition, whatever. Oh, I'm writing one. The sequence, he says this way, no 1 over n, say n going 1 to infinity is Cauchy. we are going to write the proof. Because when you write, even that is correct, I mean, there are no problems, but so this is the thing, no? For every epsilon greater than 0, for the time being, epsilon must be rational, because at his level. Then you say, for every epsilon which is rational greater than 0, there is an integer n such that for each n greater than n, blah blah blah. So you have to write let epsilon greater than 0 be an arbitrary. Get to the rhythm of writing proofs. That's the way to learn pure maths, analysis especially. Be an arbitrary rational number. Now you have done the rough work over there. Now you know what to do. Always when you are proving a theorem, you do rough work. So the proof is, in short, you say choose. You cannot write this thing without doing the rough work. When you do, you have to have rough work. Otherwise, from where on earth you get somebody may wonder. Choose capital N belongs to say he says C plus, no? Such that n greater than 1 over epsilon. Now I said this line, now I took that line. But I am writing this thing based on this work. The knowledge I have got from this rough work, that's how I am writing. Now you say, now let J according to in our way n m greater than n. Right? I took any n. Then 1 over n minus 1 over n, certainly less than 1 over capital N, certainly less than epsilon. I have got it. I took any epsilon. I mean, this is provisional for the time being, it should be rational. I choose capital N belongs to such that n greater than 1 over epsilon. Somebody may wonder why, but we know from where on earth we got that much. Now, according to here, let n greater than n. I have shown this one. Thus, according to him, he writes 1 over n going on to infinity is quotient. So it must be convincing to you. So this is how I write, but the way he is writing, he is giving the idea, everything is in the proof. So kind of difficult for a person to follow. As you can see, verifying from first principles, that is without using any of the machinery of limits, etc., that the sequence is co-sequence requires some effort, even for a sequence as simple as 1 over n. The part about selecting capital N can be particularly difficult for beginners. One has to think in reverse, working out the conditions on n would suffice to force the sequence A in A plus n 2b epsilon necessity and then finding an n which obeys those conditions. Later we will develop some limit laws which allow us to determine when the sequence is Cauchy more easily, of course. We now relate the notion of the Cauchy sequence to another basic notion of that of a bounded sequence. That is again, so these are little analysis things. Cauchy sequence, very important one, because analysis is Cauchy sequences. Follow it. Again, bounded sequences. Right. Okay. Let's see this definition of a bounded sequence. Let capital N greater than 0 be rational. I mean, he is developing a finite sequence A1 up to n is bounded by capital M if and only if mod AI less than or equal to capital M for all 1 less than it. So you have some numbers. I have very hard time with the pens now, but will it work? So you have A1, A2, A3, A4, oh, A5, like A, whatever he says, how much? A. So somewhere, if you want to say this is bounded, what does this mean? These n numbers must be in between some minus m and plus m. In between is bounded. We are bounded by the holes. In between, not in between, no? Among the holes, I guess we have 4 holes. So that is the meaning of bounded. Bounded means all the terms are in some minus m and plus m for some capital M. An infinite sequence A and M is bounded by M. Again the same thing. For all I, here if it is finite, I guess it goes without saying, no? Any finite sequence is bounded. But when you draw the picture, you can see it. But infinite sequence, that's not obvious. An infinite sequence is bounded if and only for all, if and only if AI less than or equal to M, for all I greater than or equal to M. The sequence is said to be bounded if and only if it is bounded by capital M for some rational n greater than 0. Again, this is rational but is provisional. It's for the time being. It is bounded means all the terms from a picture in some interval minus m plus m. On definition wise, mod A less than or equal to M. Example 5.1.3, the finite sequence 1 minus 2, 3 minus 4 is bounded. In this case, it is bounded by 4. No? So 4 is, or indeed by any M greater than or equal to 4. That's clear. But the infinite sequence 1 minus 2, 3 minus 4, 5 minus 6 is unbounded. Can you prove this? We are asking. Let's do it. Use proportion 4.4.1. I don't know. Whatever it is, let's do it. If I am going to prove something terribly obvious, you can say it's not needed. Because that way we can save some time. But if you need it, let me go ahead. So he wants to prove the sequence 1 minus 2, 1 minus 2, 3 minus 4, 5 minus 6. This sequence is unbounded. But he gave the definition of bounded. Bounded means a sequence is bounded. According to him, if and only if there exists a capital M, according to him, rational, greater than or equal to 0, such that every term in absolute value is less than or equal to epsilon. That's what it means. So actually this sequence is, you can, if you want, you can say this is minus 1 raised to the power n plus 1 times n. No? This is the sequence. N going on to infinity, because if you plug 1, you get 1. If you plug 2. And my first one, n. Yes, then you n plus when you plug a1, you get, when you plug 2, you get negative 2. When you plug 3, right? So this is the sequence. So you want to prove that. Again, you have to know the definition. A sequence E in, he is writing in going on in is bounded. I write BDD for bounded if and only if there exists capital M greater than 0. Now it is provisional rational such that I write this T for such that for each n belongs to Z plus according to this course mod A less than or equal to M. That's the meaning. Now, to do this problem, you have to write the definition of unbounded. What is the definition of unbounded? Definition. The sequence. Now this would be a sort of obvious for you is unbounded. I write, you should not write BDD. I'm kind of lazy and I won't save the time. If I don't live, for each M, for each capital M, greater than 0, rational, comma, very good. There exists,
n belongs to Z plus
there exists, n belongs to Z plus,
such that
very good.
mod A n is greater than n.
Very good. I mean, I'm just asking this because at the very beginning, because I'm at the beginning, you should be able to write this then. That's how we have to prove this sequence is unbounded. -1 raised to the power n plus 1 times n. So prove that -1 to the n plus 1 n is unbounded. So now we have to discuss. I mean, you are doing alone, you are not going to discuss it somebody else, but you think about it. So why it is unbounded? If you take the absolute value, we have to prove that no matter which m you choose, no matter which m you choose positive, of course it is rational, that is provisional for the time being. So anyway, let's begin the proof, but not write the proof. Let resistance X capital M greater than 0 be rational. Then what do we need to do? We have to find, so this is, then absolute value sequence will be 1, 2, 3, 4, 5, 6, this, like that. You have to show that there is an integer n such that mod A n is n. You have to prove that. It's rough work. I have been telling you. You have to prove that there is an integer, no, there exists, is it, an integer n greater than m. That's what you need to prove. If you can prove that there is an integer n such that n greater than m, we are done. Now, Kuta, how do I know that there is an integer n greater than n?
n plus plus is greater than m.
M is not an integer, Kuta. M is a rational number.
From that proposition.
From that
Archimedean.
proposition. Yeah. No, you cannot say Archimedean. From proposition 4.4. Anyway, from some proposition, let me say that way because I cannot remember these. I have a very hard time at home by looking at them. From some proposition, there exists n, there exists n belongs to Z plus such that, let me write S-U-C-H, correct spelling. N greater than M. Thus, this is unbounded. This sequence is unbounded. Always try to write precise proofs, though they are very small. That's how you get to bigger things, bigger ideas, bigger proofs. Okay, now, finite sequences are bounded. Actually, we don't need to prove it, but anyway, let's go through because it is in the book now. Every finite sequence, A1, A2, up to N is bounded. We prove this by induction on N. When N is equal to 1, the sequence is clearly bounded. If we choose capital M to be absolute A1, then clearly we have A1 less than or equal to M. So, can you see this is incorrect now again? Because according to him, M must be a rational number so far. How does he know that A1 is rational? That's why I'm saying, I mean, he's not he, whosoever wrote the book, these Indian people, they are not logical. So this is incorrect because absolute A1 may not be even every finite positive. It could be 0. No? However, it is not, we don't know that it is rational. Anyway, so without that, it is true, no? You understand what I am saying? No? Now he says, then clearly we have A1, when n equal 1, the sequence A1 is clearly bounded. Oh, if we choose capital M equals A1, then clearly we have A1. Am I telling wrong things? Then we have, then clearly we have A less than or equal to M. What? For all I.
Because N is 1, no?
So, redundant writing. Okay, so now suppose that we have already proved the lemma for some n greater than or equal to 1. I told you that's again incorrect because we have proved it for 1. Why should we suppose? No? You don't have to suppose. Anyway, he has to say now let n be an integer such that whatever this lemma is true. We now prove it for n plus 1, that is we prove for every sequence A1 up to n plus 1 is bounded by the induction hypothesis. We know that A1 up to n is bounded by some capital M greater than 0. In particular, it must be bounded by m plus mod of an plus 1. Again, we don't know that an plus 1 is rational, and on the other hand, an plus 1 is also bounded by m plus mod an plus 1. Understand the proof, no? That's clear. Anyway, idea is very clear. So there are deficiencies that he is writing. Now suppose that statement is incorrect and we don't know that A1 and A plus 1 are rational, but they are redundant for us. Note that while this argument shows that every finite sequence is bounded, no matter how long the finite sequence is, it does not say anything about whether an infinite sequence is bounded or not. Infinity is not a natural number. However, we have Cauchy sequences are bounded. Every Cauchy sequence is bounded. You can prove it, no? Yes? So I will not spend time. That's an important result, by the way. Every Cauchy sequence is bound. So it's a very, there is another side. If a sequence is not bounded, it is not Cauchy. We use it a lot. Equivalent Cauchy sequences. It's talking about equivalence. Consider the two Cauchy sequences of rational numbers 1.4, 1.41, 1.414 and so on. The other one is 1.5, 1.42, 1.415, like that. informally both these sequences seem to be converging to the same number, the square root of 2. So he is assuming that, though this statement is not very rigorous because we have not defined real numbers yet. If we are to define the real numbers from the rationals as limit of Cauchy sequences, we have to know when two Cauchy sequences of rational give the same limit. Without first defining a real number, since that would be circular, to do this we use a similar set of definitions to those used to define the Cauchy sequence in the first place. So, I mean, here, over there, he says it's kind of we getting the impression that they are going to converge to the same number, square root of 2. That I don't like it, but what to do? No? We have in the book. Definition 5.2.1. Epsilon closed sequences. Let A n, B n be two sequences and let epsilon greater than 0. Now this epsilon is not rational, right? We say that the sequence is epsilon close to Bn if An is close to Bn for each n belongs to n. That is modulus of absolute value of An minus Bn less than or equal to epsilon for each n. In other words, the sequence A0 up A1 A2 so on, epsilon close to the sequence B0 B1. If and only if n minus Bn less than or equal to epsilon for all n. So that definition is clear. Again, from over there, you need to get the, you have to be able to get the definition of two sequences are not epsilon close. So that, can you take An and Bn are not epsilon close? What would be the definition? Two sequences An and Bn are not epsilon close.
There exists an
They are existent?
eigenvalue such that
Yes.
in minus b
In absolute value.
Given that
Then
epsilon.
epsilon. Very good, but takes time. Very good. The two sequences 1 minus 1, 1 minus 1 and so on, and 1.1 minus 1.1 plus 1.1 minus 1.1. 0.1 close to each other. So I'm not going to spend time there. Eventual epsilon close sequences. Let An and Bn be two sequences and let epsilon greater than 0. We say that the sequence An is eventually epsilon close to Bn if and only if there exists an n greater than or equal to 0 such that the sequence An and Bn starting from capital N, both of them, are epsilon close. That in other words, A0, A1 and so on is epsilon close to B0, B1 of epsilon. There exists an n greater than 0 such that An minus Bn less than or equal to epsilon for all n. So the eventually epsilon close means after some points all the terms are respective terms, not all the terms, respective terms. If you take A5 from here, you have to take B5 from there. So they are at a distance at the most epsilon. That's what it means. Again, you should be able to write tell the negation very quickly. I mean, when you know, sooner or later, next week, must be very quick. I assure you say it I will give you a toffee, you give me chocolate. Then that's how you get the feeling of pureness. When you get it, I remember you are interested in engineering, you wonder, hey, this is far more beautiful. We all like beautiful things. So we go to the beauty. You may come to be a mess. You are good actually. Remark. Then I am not going to ask what is the definition of two sequences are not epsilon, eventually epsilon close. I know you can say it. You may take a little bit more time for the time being. Again, the notations for epsilon close sequences and eventually epsilon close sequences are not standard. They are not notations, they are not in the literature. Only in this book I have seen to this day, and we will not use them outside this section. Very good. That's a good thing. The two sequences 1.1, 1.01, 1.001, 1.3071, and 0.9, 0.29, 0.39, 0.9 are not 0.1 close. Because if you subtract 1.1, 0.9, you get 0.2, no? So it cannot be 0.1 close. However, the sequences are still eventually 0.1 close. You can see far away, they are going to get close to each other, and any two respective terms will be at a distance at the most 0.1. Because if we start from the second elements onwards, these sequences are 0.1 close. A similar argument shows that the two sequences are eventually 0.01 close, and so forth. Equivalent sequences, that's important. That's the important one. We say two sequences A and B and are equivalent if and only for each epsilon, rational epsilon, now he is bringing rational again, greater than 0, the sequences A and B and are eventually epsilon close. For any rational number epsilon, the two sequences are epsilon close. In other words, A0, A1 and so on, and B0, Bn are equivalent if and only for every rational epsilon greater than 0, there is an integer capital N such that mod A n minus Bn less than or equal to epsilon for all n greater than or equal to n. Can you see another thing is, though he writes mod of A n minus Bn less than or equal to epsilon, if you want you can write mod A n minus Bn is strictly less than epsilon. It does not matter. Remark, these are clear, no? As with definitions 5.1.8, the quantity epsilon greater than 0 is currently restricted to be a positive rational rather than a positive real. However, we shall eventually see that it makes no difference whether epsilon ranges over the positive rationals or positive real. See exercise 6.1.10. From the definition 5.2.6, it seems that the two sequences given in example 5.2.5 appear to be equivalent. We now prove this rigorously. He is going to say A n is 1 plus 10 to the minus n. So A1 is 1.1, no? 10 to the minus 1 is 1 over 10, no? Then 1.1, 1.01, like that. Bn is, you are subtracting 0.1, then you get 0.9, 0.99, like that. Then the sequences A and Bn are equivalent, no? Again you can do this, no? No need to spend time. So I am not going to go through the proof. I am not spending time with the proof. No problem, no time. Then you have exercises. A and B n are equivalent sequences of rationals. A n is Cauchy if and only B n is Cauchy. That's a good exercise. So that A and B n are eventually close, then A n is bounded if and only B n is bounded. Now comes to the construction of the real numbers. So way to go, no? We are now, anyway, now we constructed the natural numbers which included 0, and then he used Peano axioms, he called them Peano axioms. then he used actually principle of mathematical induction as an axiom. In my book, I didn't bring the book, I have proved the principle of mathematical induction, so I am assuming some things that which he is not assuming. We are not ready to construct the real numbers, so we have first constructed the natural numbers, then integers, then rationals. Now, at the most important thing, real numbers. We introduce a new symbol, LIM, because we haven't discussed limit yet. Similar to the formal notations, long dash and double parallel lines defined earlier. As the notation suggests, this will eventually mesh the family operation of lim. Then he is assuming, oh, you already know lim, no, familiar, how can you say? At which point the formal limit symbol can be discarded. Okay. Now let's see real numbers. A real number is defined to be an object of the form capital L, capital I, capital M, n arrow infinity, an, because we don't know meaning of any of those. It's just a object or a symbol. A capital L, capital I, capital M, n arrow infinity, an, where a and n going on to infinity is a Cauchy sequence of rational numbers. We know with the meaning of that. So for a sequence of Cauchy sequence of rational numbers, we are going to attach this lim and n tends to infinity a. So, but we have no idea about lim n tends to infinity a. That's why he says a real number is defined to be an object of the form. That. However, all we know is an is a Cauchy sequence. Two real numbers, lim n tends to infinity, an and lim n tends to bn are said to be equal if and only if an and bn are equivalent Cauchy sequences. Equivalent means we went through the definition, no? They are equivalent. So, the two real numbers lim bn are said to be equal if and only if these two sequences are, co-sequences are equivalent, that we know of the meaning. But again, he has informal here. Let A1, A2, A3 denote the sequence 1.4, 1.41, 1.414, etc. And let B1, B2, B3 denotes the sequence 1.5, etc. Then lim n tends to infinity an is a real number. N is the same real number as lim n tends to infinity bn because a and bn are equivalent Cauchy sequences of rational numbers. That's important because 1.4, 1.41, all of them are rational. 1.5, 1.42, that's also rational. And here he says informal because we don't know the meaning of lim. However, I guess we are expecting or guessing or forecasting, I don't know the right word, there is no right word by the way. That's both of them limit is square root of 2, that's what he is guessing. And is same as the real number as this thing because are Cauchy sequences. Right? Now when he writes lim n tends to infinity an equals lim n tends to bn, you know two things. Both an and bn are rational sequences. They are Cauchy sequences and they are equivalent sequences. Then we write this thing. But do we know anything about this LIM business? No. Something related to that we know is that these two sequences both are Cauchy, which are equivalent. We will refer to them n tends to infinity n as the formal limit of the sequence an. He is using the word formal limit. I don't know. To me, I'm a little bit uncomfortable because the reason is we know the meaning of limit. without knowing anything about the limit here, he is saying we will refer this thing as the formal limit. I mean, without knowing anything about the limit. He says, I am uncomfortable, I don't know about you. Later on, we will define a genuine notion of limit and show that the formal limit of a cosequence is the same as the limit of that sequence. Now, the thing to me, problem is actually what is, I mean, that's just a symbol. How can he say it is a formal limit? To me, I am not on the fence. I am on the other side, completely. If you say you are on the fence, you have to sort of in that side, no. Anyway, so let's go through. We will refer to lim inference as a formal limit of the sequence A later on. So now what you need to remember is this formal limit is this symbol. Capital lim n tends to infinity A. We will refer to this thing as the formal limit. That's the formal limit. Later on we will define the universal limit and show that the formal limit of a sequence is the same as the limit of that sequence. That's the place where I get uncomfortable. Actual limit you learn, you study, you find formal limit. I mean, this is for two cosequences. If it is a cosequence, you just write in front of that lim. I don't know. Same as after that, we will not need formal limits ever again. Thank you very much. The situation is much like what we did with the formal subtraction, round dash, and formal division, double parallel lines. So you have to be kind of patient to follow this book because of what he is doing. In order to ensure that this definition is valid, we need to check the notion of equality in the definition obeys the first three laws of equality. Formal limits are well defined. Let x be limit a n, y be limit b n. This formal limit, we don't know what it means. And let z equals limit c n be real numbers. Then with the above definition of equality for real numbers, we have x equals x. X equals x means an sequence
equal to A sequence.
equivalent to the an sequence itself. Then also if x is equal to y, then y is equal to x. Again, if an is equivalent to bn, then bn is equivalent to an. That is also sure. No? Finally, if x equals y and y equals z, then x is equals to z. Then we have to prove if x an is equivalent to bn and bn is equivalent to cn, then an is equivalent to cn. That can be proved very easily. So Cx less 5.3.1, that's also done then. Because of this proposition, we know that our definition of equality between two rational numbers is legitimate, he says. Okay. Of course, when we define other operations on the reals, we have to check that they obey the law of substitution. Two real numbers, inputs which are equal, should give equal outputs when applied to any operation on the real numbers. Now we want to define on the real numbers all the usual arithmetic operations such as addition and multiplication. Now we have real numbers, no? This formal limit. Now we want to define the real arithmetic operations such as addition and multiplication. We begin with addition. Let's see what he says. One gets tired of doing this thing actually. Anyway, I mean, after this chapter it's going to be much less. Addition of reals. Let x is lim a n, y equals lim b n be real numbers. Then we define the sum x plus y. To b, he is defining lim a n plus b n because he can define this thing. If a and b n are both rational, a n plus b n is also rational. And if a and b n are quotient, a n plus b n is also Cauchy. I wonder whether he proved that before. Addition of two Cauchy sequences is Cauchy.
Probably exercise or something.
Yeah. Assume anyway, we can prove it. The sum of limit 1 plus 1 over n and limit 2 plus 3 over n is limit 3 plus 4 over n. So he is assuming that 1 plus 1 over n, I can see that they are rational right away. And of course both of them are Cauchy. As a result he can add, and that is the thing. Anyway, he defined addition of real numbers. We now check that this definition is valid. The first thing we need to do is to confirm that the sum of two real numbers is in fact a real number. That means addition of, here he goes. Here you go. The sum of Cauchy sequences is Cauchy. Let x equals lim a n, y equals lim b n, then x plus y is also a real number. That is, a n plus b n is a Cauchy sequence. We can prove it very easily, so I am not going to, no need to spend time. No need to spend time. Do we have to go through? No. The other thing we need to check is the axiom of substitution. See section A.7. If we replace a real number x by another number equal to x, then this should not change the sum x plus y. And similarly, if we substitute y for another number equal to y. So what does he say? The construction of the real numbers, still we are going. Sum of equivalent Cauchy sequences are equivalent. Again, I guess we don't need to go through, no? Kutala? But if by any chance somebody says like this, you don't have to agree if you don't understand. That's, mathematics is like that, because some people, when I told this one Chinese boy in US, he's like a kid, but he's smarter than all the students in our class. Yeah, even the professor asked him, would you like to come to Ohio State to do a PhD? Who wants to come to Ohio State? He replied like that. Okay, here sums of, anyway, what he is proving is sums of equivalent Cauchy sequences are equivalent. We can prove it, this is no big deal. The above lemma verifies the axiom of substitution for the x variable in x plus y, but one can similarly prove the axiom of substitution for the y variable. A quick way is to observe from the definition of x plus y that we certainly have x plus y equals y plus x. So actually we don't need to go through that because of that thing. Definition 5.3.9 is multiplication of reals. Let x is lim a n, y equals lim b n real numbers, then we define the product xy to be lim a n b n. However, here there is a problem, because a n is Cauchy, a n is rational, b n is rational, therefore a n b n is rational. A n is a Cauchy sequence, b n is a Cauchy sequence, then a n b n is a Cauchy sequence. We have to prove it, otherwise we cannot write. The following propositions ensures that this definition is valid and the product of two real numbers is in fact a real number. Multiplication is well defined. Let x equals lim a n, y equals lim b n, and x dash be real numbers, then xy is also a real number. Before that he has to say xy is a real number. Let's see this exercise. What does he say? Exercise 5.3.2, no? 5.3.2. Exercise 5.3.2. He says hint again. It's yeah. Because exercise 5.3.2, I just look at it, this says hint again. Proportion 4.37 may be useful. I mean, before that, actually before he writes the definition 5.3.9, he has to prove that product of two Cauchy sequences is Cauchy. Again, he is not mentioning it here. That's not good. Anyway, you can prove it, no? Can you? Can somebody tell me how to prove it? Because that is. That's it. Because it is different from addition of two Cauchy sequences is Cauchy is easy, but the product is not. That way, I guess. Let n going 1 to infinity, n going 1 to infinity be two rational Cauchy sequences. Then n going 1 to infinity is a rational Cauchy sequence. Okay, yeah. Putha, how do we prove this thing? Proof. What do we have to prove, by the way? Putha, what do we have to prove? In order to prove that A and B is a Cauchy sequence, what do we have to prove?
For some n greater than capital N,
Greater than 1.
in
Putha, what? Eventually, steady. So, in here, what do I have to do? Anyway. What's the definition? Using our symbols, words, and etc. Something is a Cauchy sequence. I guess I wrote the definition on the board some time ago and I erased it. Putha,
There exists the symbol n greater than or equal to 1 such that for all epsilon greater than 0 and for all epsilon greater than 0 aj bj minus a k bk mod is less than or equal to epsilon for all jk greater than or equal to m.
so in the proof, what is the first thing I should write? First statement. Anyway, all four, 3 people replied, answers are not satisfactory. Not satisfactory. What you need to prove is for each epsilon greater than 0, there is an integer capital N greater than or equal to 1, such that for each jk greater than n, absolute value of ajbj minus akbk less than epsilon. Right? So, all are not satisfactory. Anyway, so from what I said, what should be the first thing I should write? This is a homework problem. Shall I leave it as homework or shall I do it? What do you say?
Doing here is good, I guess.
Okay, so let's do it. So what is the first thing? I told you the definition or no? So Buddha, what should I write my first line?
Let epsilon.
Very good, very good, very good. Let epsilon greater than 0 be arbitrary or be arbitrary. If you want, we can write Russian. Arbitrary. Let's write rational also. I mean, it's redundant for us, but to be consistent with the book. Now, I need what? A capital N. Now, rough work here. Capital N such that I need capital N belongs to Z plus such that for each jk greater than capital N, aj, bj minus ak, bk must be less than epsilon. That's what we need. I wrote epsilon greater than 0. I need a capital N such that this. However, since I have written epsilon greater than 0 be arbitrary, since an is rational, there is something I can say. What can I say? Since n going on to infinity is Cauchy. Kuta, what can I say?
For epsilon A is eventually very.
No, I have already written epsilon greater than 0. Thereafter, you cannot write for all epsilon.
A is eventually.
Your homework is getting marked. That's very important. I got the impression that the way he is saying, so far you did not get. Maybe we should shoot Putra Prabhat. Since n is Cauchy, and we are given epsilon or Buddha, thereafter you cannot say, in this proof, you cannot use the word for each epsilon hereafter. Since n is Cauchy,
A is eventually epsilon state.
okay. No, I told you no. Like this. Am I going very fast? No. I told you n is Cauchy if and only if according to the book. For each epsilon greater than 0, there is an integer n such that for each jk greater than n, absolute value of aj minus ak less than epsilon. So, according to that, since n is Cauchy, there exists, this time it is coming out, but pen is not working. There exists, let's say, because we have two Cauchy sequences now, I will use here n1. n1 such that
For J1, K1 greater than N.
for all j, let me write say j, jk. I can see why you said j1, k1 because
Yeah,
of the
this
two
one,
sequences. For all jk greater than n1,
AJ minus
aj minus
AK on this
less than epsilon. So this is what we have. Also, since b n n going to 1 to infinity is Cauchy, they are like this. n2, I did not write here n1 belongs to Z plus. such that for rho jk greater than into what? Bj minus bk in absolute value. Here I is less than or equal, by the way. I have always write, Sri Lankans write less than Vk minus Vk, less than epsilon. These are the things we know. 5 more minutes to 11. Now, you have n1 a positive integer, n2 another positive integer. After n1, distance between any two edges is less than epsilon. After n2, distance between any two bj's is less than epsilon. Now what we need here is, we need the n, not n1, not n2, because n1 and 2 don't work very well. After n, this thing must be less than epsilon. Now I'm not going to write the proof right away, but how are we going to get it? Alright. So, you know what we need is a capital N. Here, this is what we need. We need an n belongs to Z plus, which satisfies this condition. So, I brought into your attention that we should add minus ajbk plus ajbk, etc. Then we come to this level. Now you can see, you know that Cauchy sequences are bounded. Therefore, say this one may be less than or equal to m1 for each n belongs to n, for each j belongs to n. Similarly, this one may be bounded by m2. So if you want, you can use capital A and capital B because ajbk. So then if you make this whole thing less than epsilon by 2 and this whole thing less than epsilon by 2, sum is less than epsilon. So if you want this to make this thing to be less than epsilon by 2, now bj, aj less than or equal to say m1, then you have to make bj minus bk less than epsilon by 2 times m1. So m1 cancels each other. Similarly here. So at the very beginning then, now I have written here, since this is Cauchy, this one less than epsilon. Now can you see? This line cannot be used in the proof now. Because these are my rough work. I have learned that aj minus ak, I have to make sure aj minus ak less than epsilon by 2 times m2. So I have to, because of the rough work, I am getting this. So I will erase this. Everybody understands what I am doing, no? Since xn is Cauchy, let's say there exists m1. And you see now that's what we need first. You learn that from your rough work. There exists n1 greater than 0 such that do I have to write since n is Cauchy, n is bounded? No, you don't have to. There exists n1 greater than 0 such that mod an less than epsilon by 2 times M1. Oh, no. I did so. MC. For each n belongs to n. That is because co-sequences are bounded. Also since, let's start from here, also since Bn is Cauchy, is missing here. There is M2 greater than 0. Such that this is the problem. No? Let's see. This is the problem. Okay, greater than 0 such that. Again, I am writing in the parabola like this, such that mod of Bn is strictly less than M2 for each n belongs to n. N belongs to, for us, is n plus no? In this course. Right? Now I am going to use the fact that also since, again also since n is Cauchy, there exists n1. Belongs to Z plus such that, let me write such that, for each, let's say Jk greater than n1, Aj minus Ak is strictly less than epsilon by 2 times. Here I need M2. Can you see? Besides, since Bn n going on to infinity is Cauchy, there it is n2 belongs to Z plus, such that for each Jk greater than n2, Bj minus Bk is less than epsilon by m1. I am writing all this based on this rough work. No? Now I will say, now let n is equal to maximum of n1 and n2. I take the maximum of n1 and n2. Right? Now I want to prove that line. Let J, K be greater than n. Right? Now I am going to show that Aj, Bj minus Ak, Bk less than epsilon. That's what I am going to do. Now let Jk greater than n, then Jk greater than n1 and Jk greater than n2 both, because n is the maximum. Notice that Aj, Bj minus Ak, Bk is equal to, I am going to insert minus past that term, AJ, BJ minus AJ, BK, AJ, BK plus AJ, BK. Right? So, last term I have written minus AK, BK. This is equal to AJ times BJ minus BK plus BK times AJ minus AK. Right?
You can move the chair.
Eh?
You can move the chair, please. Chair.
And this is less than or equal to, I will write at once absolute mod AJ, BJ minus BK plus mod BK, AJ minus AK. Right? But this is strictly less than. I have written, to follow the book, let's say less than 1 every year. Let's have the book that too. Less than or equal. Mod AJ, yeah, less than M1. Mod BJ minus BK less than epsilon divided by epsilon 2 times M1. Mod BK less than or equal to M2. Then mod AJ minus AK less than epsilon 2 times M2. So this is equal to epsilon by 2 plus epsilon by 2, which is equal to epsilon. No, so what I have done, I have written let epsilon greater than 0 be arbitrary. I have find the n, capital N, and I have taken any jk greater than n. Then I have shown that AJ, BJ minus AK, BK in absolute value less than epsilon. Hence, AJ, BJ, OA and BN, n going 1 into is quotient. So this is the proof. So this sort of things are needed when you are proving things. Here we use the fact that Cauchy sequences are bounded, and the strength of any epsilon. Because when you say, though you write 1 epsilon, A minus Bn less than epsilon, here I have used over there epsilon over 2 times M2, over here epsilon 2 times M1. Finally somehow I have got epsilon. So we have shown that product of 2 Cauchy sequences is quotient. So you need, in analysis you do this kind of things a lot. So that's why I'm saying when you are working with the book, this sort of things are forgotten, and we are worried about proposition 4.1.1. This and that. Alright, let's go. Anyway, we spend a lot of time, but you all understood, no? The proof. I suppose, he says that multiplication is well defined. I guess you can understand, he has not written the proof. Cx dash 5.3.2. I think you can do it, it's no big deal. Again, of course, we can prove similar substitution rule when y is replaced by a real number y dash which is equal to I, the same idea. At this point, we embed the rationals back to reals. Now, we are defining reals using rationals. Every real number is about us so far is a lim, formal limit is lim, n tends to infinity, an where n going to 1 to infinity is a Cauchy sequence. That's how we define. Now here he wants to make sure real rational numbers are actually real numbers. So he is, at this point we embed the rationals back into the reals by equating every rational number q with the real number lim n tends to infinity q. So, for instance, here actually, if you write a sequence q, that is a Cauchy sequence. Q is rational. When you write q, he hasn't mentioned that. But anyway, I am pointing out it here. You understand what I am saying? Q, that is a sequence with every term is q, is a Cauchy sequence because distance between any 2 points of the sequence is 0 actually. For instance, if at A1, A2, A3 is the sequence 0.5 continuously, then we set limit an to be 0.5. We set this thing to be equal to 0.5. This embed is consistent with our definitions of addition and multiplication, since for any rational numbers a, b, we have lim a plus lim b is, it works according to our embedding. So this way anyway we have defined real numbers, and inside that we have embedded rational numbers. Every rational number is this sort of formal limit of, if you take the rational number q is formal limit of lim n a n, lim n tends to infinity q. So
actually he used intuition to explain that definition, no?
I'm sorry?
He actually used intuition to explain that definition, no? So
Yeah. No, we are using our knowledge to define and then say, okay, that works. That's what we are doing here. That's what we are doing. This means that when one wants to add or multiply two rational numbers, a, b, it does not matter whether one thinks of these numbers as rationals or as the real numbers lim n tends to infinity a. It doesn't matter. However, one thing is important here, we set lim n tends to a to be 0.5. That's what we are doing. We don't know that thing has a limit. That's why he said we set. We don't know the limit. So it doesn't harm anything, actually it tallies with our expectations. That's the thing. Also, this identification of rational numbers and real numbers is consistent with our definitions. We can easily define minus x. Minus x is say minus 1 times x, because if x is a real number which is a Cauchy sequence, then that's how we have to limit. Think minus 1 times x is minus x. Since minus 1 is a rational number and hence real, note that this is clearly consistent with our negation of rational numbers, since minus q is minus 1 times q for all rational numbers q. Also, from our definitions it is clear that minus lim n tends to infinity is limit. Let's see whether it is clear, because lim n tends to infinity is, we have a Cauchy sequence a n, so left hand side is negative Cauchy sequence. No? Right hand side is also definitely, you have the negative Cauchy sequence. He is asking why, we reply. Once we have addition and negation, we can define subtraction, of course. Now you can guess even without his writing. Note that this implies limit of an minus limit of bn is this way, and x is lim n an, y is lim n bn, then lim n goes to x plus minus y is x is an plus minus y is minus bn. So we can now easily show that the real numbers obey all the usual rules of algebra except perhaps for the laws involving division, which shall address shortly. He says other decision, especially not decision. Especially addition and multiplication and negation, subtraction. All the laws of algebra from proposition 416 hold not only for the integers but for the reals as well. I am not going to go through it because I guess once you read it you can understand. Am I correct? Sure, no? Here, the last basic operation we need to define is reciprocative. Reciprocation. What is it? X goes to x minus. This one is a little more subtle. The obvious first guess for how to proceed would be define lim an inverse is, this is how we think, no? X is lim, capital lim and tends to infinity an, then its inverse should be this is the first thing which comes to our mind, lim and tends to infinity an inverse. Then he says, but there are few problems with this. For instance, let a1, a2, a3 be the Cauchy sequence 0.1, 0.01 and so on, and let x equals this thing, then by definition x inverse would be lim bn, where b1 up to bn is the sequence. Ten, 100,000, this and that, but this is not a Cauchy sequence. It isn't even bounded, because we know what is Cauchy sequences are bounded. Then if it is not bounded, it cannot be Cauchy. Of course, the problem here is that our original Cauchy sequence was equivalent to zero sequence. That is the problem. 0.1, 0.01, 0.001. Though no term is zero, whole sequence is equivalent to 0, 0, 0 Cauchy sequence. That is the problem here. But this is not a Cauchy sequence, it is answer. And hence that our real number x was in fact equal to 0. Our x is 0 because here, who is this? Hence our real number x was in fact equal to 0. So we should only allow the operation of reciprocal when x is non-zero. So can you see, if you take equations, Cauchy sequence equivalent to 0, then you run into trouble. X inverse is going to be unbounded sequence always. However, even when we restrict ourselves to non-zero real numbers, we have a slight problem, because a non-zero real number might be the formal limit of a Cauchy sequence which contains zero elements. You can have no zero elements here and there. For instance, the number 1, which is rational and hence real, is the formal limit 0.9, 0.99, like that. Where am I?
And let x equal limit and goes to
I press different things, you know. Where do we have when here, okay. Which is rational and hence 1, real number 1, the limit of that sequence is 1, no? I mean, you know that actually, no? But using our, I have to say something here, because 1.000 like this is equal to 0.99 like this. this one tells you something very important. You cannot say nth decimal point of a real number. These are two real numbers, they are equal. Nth third decimal point of, if you use this expansion, third decimal point is 0, here third decimal point is 9. So nth decimal point is not 25. You know that these two are the same, no? Do you? Do you know? Can you prove it?
Yes.
How?
Take 0.99 something as x,
Uh,
multiplied by 10, then subtract 10 you get what's equal.
Okay. So, did you get what I said? Nth decimal point, you cannot say let a and be the nth decimal point of some number. That's not 25. Alright, you can make it. That's one reason that real number system is not defined using decimals, even though we are using decimal always. Alright, okay, of the co-sequence, but using our naive definition of reciprocal, we cannot invert the real number 1 because we aren't invert the first element 0 of this Cauchy sequence. Alright. To go around these problems, we need to keep Cauchy sequences away from 0. We need to go away from 0. To do this, we first need a definition. Sequences bounded away from 0. What? A sequence A of rational numbers is said to be bounded away from 0 if and only if there exists a rational number C greater than 0 such that mod A greater than or equal to C for all A. I'm getting tired. මේ bounded away from 0 කියන පැටියෝ මේ දැන් sequence එකක් bounded away from 0 කියන්නේ 0 මෙතන නම් මෙතන C මේ පැත්තේ දැන් equal to 1 but A can be negative. A can be negative, however mod A must be greater than or equal to C where C is a positive number. Did he say? Yes. Rational number C. The sequence 1 minus 1, 1, 1 minus 1, etc. is bounded away from 0. All the coefficients have absolute value 1. But the sequence 0.1, 0.01, etc. is not bounded away from 0. And neither 0.09, 0.99, etc. The sequence 10, 100,000 is bounded away from 0 but is not bounded. Anyway, that goes without saying. We now show that every non-zero real number is the formal limit of a Cauchy sequence bounded away from 0. Important result. Because now we are in the process of defining x inverse. So we know that x must be non-zero in order to define x inverse. So we are using our real numbers are, so far we have no idea, this capital lim, blah blah blah. So in order to define, if you take a number x which is not equal to 0, it must be a formal limit of some xn or some an bounded away from 0. Otherwise we cannot define. So this is, lemma is important one. Let x be a non-zero real number, then x is lim an for some Cauchy sequence which is bounded away from 0. Of course, there are sequences, Cauchy sequences, Bn, 0 may be there in that one, here and there. But definitely there exists a sequence An for some Cauchy sequence An which is bounded away from 0. So if x is non-zero, since by this lemma, since there is a Cauchy sequence bounded away from 0, then we can define x inverse or reciprocal of x. This is an important result. I mean, for the time being, after we are done with this, we are not going to worry about it anyway. For the time being, we are constructing now. Since x is real, we know that x is lim Bn for some cosequence Bn. Of course, it goes without saying. But we are not yet done, of course, because we do not know that Bn is bounded away from 0. Every real number is a formal limit of some cosequence Bn. That's why he said, since x is real, we know that. But we are not done, he says, we don't know whether or not Bn is bounded away from 0. On the other hand, we are given that x is not 0. We know that x is not 0. However, 0 is lim n tends to infinity 0. Which means that the sequence Bn is not equivalent to 0 sequence. Since x is not 0, Bn cannot be equivalent to 0 sequence. The sequence Bn cannot be eventually epsilon close to 0 sequence for every epsilon greater than 0, since it is not equivalent to 0 sequence. Therefore, we can find an epsilon greater than 0 such that Bn is not eventually epsilon close to 0 sequence. That is the important thing. Bn is not eventually epsilon close to 0 sequence. We got that. Why? Because x is not 0. There is such a such an epsilon. Then he is, put in details. Shall I go through them? Oh, but if you want, I can go through. If I don't go through, sometimes I may say, okay, this is okay, this is okay. Then I will cover whole book. If you want me to, I can discuss. Okay. Now he is fixing epsilon. Let's fix epsilon. We know that Bn is a Cauchy sequence. So it is eventually epsilon steady. Moreover, it's eventually epsilon by 2 is steady, and that's, of course, it goes without saying, since epsilon by 2 greater than 0. Thus, there is an n greater than or equal to such that Bn minus Bm less than or equal to epsilon by 2 for all nm greater than n, because that comes because it is eventually epsilon by 2 steady. Actually, it is because it is a Cauchy sequence. We got this line. On the other hand, we cannot have Bn less than or equal to epsilon for all n greater than or equal to n. If so, it is going to be equivalent to 0. No? Since this would imply Bn is eventually epsilon close to 0. Okay, he said that. Thus, there must be some n0 greater than or equal to n for which Bn0 greater than epsilon. There must be at least one n0. Since we already know that Bn0 minus Bn less than or equal to epsilon by 2, for all n greater than n, we thus conclude from the triangle inequality, he is asking how, Bn greater than or equal to epsilon by 2. Can you do that, by the way? Now Bn 0 greater than epsilon. I know Bn minus Bm less than or equal to epsilon by 2 for all nm greater than n. Can I say that we thus conclude from the triangle inequality? You know, triangle inequality is sometimes this chair is also like the book. It goes, they improve on how I want it to move. Exercise.
5.3.1.
I cannot put on you. Whole board. Here, what he said was, we cannot have Bn less than or equal for all n greater than or equal to n. No, then Bn will be, since this would imply that Bn is eventually epsilon close to 0. No, it cannot happen. Thus there must be some n0 greater than or equal to n, for which now we have at least one n0 for which Bn0 is using greater than epsilon. One of them. Since we already know that Bn0 minus Bn, however, Bn0 minus Bn, this is less than or equal to epsilon by 2 for each n greater than or equal to n. We thus conclude from the triangle inequality. Here he is saying, then from here he is saying we can conclude Bn greater than or equal to epsilon by 2 for all n greater than or equal to n. He is saying from triangle inequality. Can you do it? That's what I am asking. Now, Bn0 greater than epsilon, and you know this thing Bn0 minus Bn less than or equal to epsilon by 2. Then he is saying for all n greater than or equal to n, Bn greater than or equal to epsilon by 2. I mean, this has nothing to do with the analysis. I mean, can you say why? The things we know are absolute value of A minus absolute value of B less than or equal to absolute value of A minus B. Oh, and this is triangle in mod A plus B less than or equal to mod A plus mod B. These are the things we know. From here, can you prove it? I mean, it's a O-level problem, but I am asking you, which is right.
Bn naught minus Bn mod is less than or equal to Bn naught mod plus Bn mod.
Could you say, start from beginning?
Bn naught minus Bn absolute value
Bn0 minus Bn absolute value
is less than or equal to
Bn0 minus
Bn naught mod plus Bn mod.
this is true.
So
This is for any n. Therefore, mod Bn greater than or equal to Bn0 minus Bn minus Bn0. That's what we can get. Bn0 minus Bn greater than or equal to epsilon by is less than or equal to epsilon by 2. So, yes,
Bn naught is the minus part.
yeah.
this goes like this. So then Bn0 minus Bn less than or equal to epsilon by 2. Then how? Sometimes even a little thing can give you a hard time. How can we do? These are the things we know. What we can say, mod of A minus mod of B less than or equal to mod of A minus B. Or mod of B minus mod of A less than or equal to mod of A minus B. These are the things we can say. Now here we want to prove, these two are the same, no? Though I wrote like two different ones. How can we do it? From here, if you want, you can get mod B minus mod of A minus B less than or equal to mod A. If you want, now you can replace this thing by mod B n, A is by mod B n, then B by mod A, no? These are the ones. No, mod B n 0. Then this one by mod B n 0, mod B n 0 greater than epsilon, mod B n minus B 0 less than or equal to epsilon by 2, therefore minus greater than or equal to minus epsilon by 2, which is equal to epsilon by 2. Right? That's why I am asking you to do every little thing. Sometimes very little things can give hard time. Because the reason is not because of you are not good, simply because of you are not used to this kind of thing so far. Two things is playing a role now here. You have to be able to logic. This one is clear now, no? You have to be able to logically write and logical thinking. Two things. Then previous one we were proving. We added and subtracted minus A, B, K. That sort of thing plays a big role here. Anyway, right now, no? Correct, no? So the reason I asked you to do it, because I know, though it is very simple, sometimes you cannot do very simple things. Alright. So, where am I? Not in the book. Anyway, so now we have proved Bn greater than or equal to epsilon by 2 for all n greater than or equal to n. He says this almost proves that Bn is bounded away from 0. Almost. Let's see why he says that. Actually, what it does is show that Bn is eventually bounded away from 0. That's what it says. Because it is only after capital N, no? Mod Bn greater than or equal to epsilon by 2 after capital N only. We have shown. So that's why he says this almost proves that Bn is bounded away from 0. Actually, what it does is show that Bn is eventually bounded away from 0. But this is easily fixed, he says, by defining a new sequence An by setting An equal to epsilon by 2 if n less than n and An equals Bn if n greater than n. Since Bn is a Cauchy sequence, it is not hard to verify that An is also a Cauchy sequence. Can you see what he did? We have shown that Bn is greater than or equal to epsilon by 2 for all n greater than or equal to n. But then we don't know what happens at the beginning. So what he does is he is defining a new sequence An. An is epsilon by 2. If n is strictly less than n, then An is equal to Bn if n greater than or equal to n. Now, since Bn is Cauchy sequence, this A will also be a Cauchy sequence. Because first, I am saying always, when you are thinking of sequences, first n terms, first 100 terms, first 1000 terms are redundant. So now this new sequence is a Cauchy sequence, which is equivalent to Bn, because the two sequences are eventually the same, and so x equals to limit of an, and since Bn greater than or equal to epsilon by 2 for all n greater than or equal to n, we know that mod n greater than or equal to epsilon by 2 for all n by first capital N terms, any of them is epsilon by 2. After capital N, any term is greater than or equal to epsilon by 2. Therefore, in the sequence An, every term is greater than or equal to epsilon by 2. We know that splitting into the two cases n greater than or equal to n and n less than n separately, and less trivial. Thus, we have a Cauchy sequence which is bounded away from 0 by epsilon by 2 instead epsilon. But that's still okay, since epsilon by 2 greater than 0 is s, and which is as x as a formal limit, and so we are done. I guess it didn't, though I wrote you understand line by line, you didn't get the message, I guess. I have that kind of feeling. Did you get it? Now, what he did was, he altered the sequence. Because x is not 0, it is not equivalent to 0 sequence. Therefore, he used at least one term, and Vn0, which, because it is epsilon steady or whatever, epsilon close, Vn at least one term, Vn0 greater than epsilon, there must be, no? Then he used that one to construct, he used that first to prove that after capital N, every term must be greater than or equal to epsilon by 2. Then he is constructing a new sequence. First capital N terms are epsilon by 2, after capital N, Bn. So, Cauchiness and eventually whatever the words he is using are kept, because for any sequence, very first n terms, 1000 terms, million terms don't play any big role. But I guess you should read it again to make sure what he did, because this is the first time he altered the sequence. But the required qualities remain the same. That's what he did. That is the thing. He began from a sequence Bn. He changed the first capital N terms. Again, Cauchiness, nothing will happen. Then epsilon steady or epsilon closeness, nothing will happen. Eventual behavior remains the same, no? Because if you take, say, suppose I take a sequence, first term is 10, next term is 10, third term is 10, fourth term is 10. I check, sorry, thousands term is also 10. This is thousands, please. Then check, I go to billion term, that is also 10. This is billion. So I am telling, I tell the person, I have a sequence, first term is 10, second term is 10, third term is 10, fourth term is 10, 100 term is 10, I go all the way, check, billion term is 10, then I ask him, what about the next term? What is the next term? Next term can be 0. Because it doesn't matter, I mean, if you ask a person, however, not in this class, then he will say it goes without saying that the next term is also 10. It doesn't have to be. So, I would recommend you to go through this again, and I myself will come back to it, because it is very important Because that's how we define reciprocal, no? The word he using for in our words, x inverse of a non-zero number. Because what he did was, it's very important. If you take a non-zero number x, it is a formal limit for non-zero sequence of rationals. Otherwise you cannot do it. That's what he did here. So it's not a difficult thing, but to you, because you are beginning, it's kind of difficult, I guess. I mean, these kind of things are also, that's why I am saying he's focusing on not the things that we are very important in an analysis class. It's, other things, but what to do, no? We have to go through. Then what he says, once a sequence is bounded away from zero, we can take its reciprocal without any difficulty. Again, we should come back and talk about it again. I want to make sure you understand. I will please read it again. I will ask questions about it next day, because this is the first time he altered the sequence. So you should understand it. Suppose an is a cosequence which is bounded away from zero, then the sequence an is also a cosequence. That again, he has proved it, no? Let's see his proof. He has written. Okay, that's good. But still I will go through it. Since an is bounded away from zero, we know that there is a c greater than 0 such that mod n greater than or equal to c for all n. That's true, no? Now what we are going to prove is, if an is Cauchy and if an is bounded away from 0, then an inverse is also Cauchy. I am acting like that lecturer, with my hands. You were not there, unfortunately. He was saying, like this, no? Everything he did by hands. You understand? I have a sequence bounded away from 0, sequence A. Now I want to say an inverse is a Cauchy sequence that is bounded away from 0. That's what we are going to do. An is also a Cauchy sequence, which is, most important thing is, it's a Cauchy sequence. If an is Cauchy bounded away from 0, an inverse is a Cauchy sequence. So it's easy to prove, very easy actually. We need to show that an is eventually epsilon necessary for each epsilon greater than 0. So thus let us fix an epsilon greater than 0. Our task is now to find n greater than or equal to such that an inverse minus am inverse less than or equal to epsilon for all nm greater than or equal to n. Clear? How shall I write on the board? So this one is simple. He is simplifying, but an minus am inverse is a minus an over mn, and an all are greater than or equal to c. Therefore 1 over is less than or equal to c square, since an greater than or equal to c. And so to make an inverse minus am inverse less than or equal to epsilon, it will suffice to make an minus an less than or equal to epsilon, c square times epsilon. That can be done. Kutai, do you understand, or shall I write separately on the board? If you say yes, I will. I mean, to some of you it may be clear, but to you it may not be. Okay, let me write. Right. This chair, sometimes it is very helpful when I want to sit for a while, because when I am reading the book. This time I can tell you. You should try to get into the, but still we are proving little things now. We are proving. What we are going to prove is this now. You have a sequence an n going 1 to infinity. This is bound away from 0. Away from 0 and n is quotient. Right? You have a sequence an is bounded away from 0 and an is quotient. So what do we need to do? Need to show that an inverse is quotient. That's what we need to do. So proof. So a sequence A, whatever sequence xn is quotient, if what? For all epsilon greater than 0, there exists an integer in capital N belongs to n, such that for each nm greater than n, mod of xn minus xm less than epsilon. This is the meaning of a Cauchy sequence. So according to this, I have to start from, what's the line for that? Let, very good, let epsilon greater than 0. Now I need a capital N, such that how an inverse minus am inverse must be less than epsilon. Sorry, I need a capital N, yes, I said what I said is correct. I need a capital N such that if I take any n and any m bigger than capital N, then an inverse minus am inverse must be less than epsilon. So here I am writing, now this is, now this time I am going to rougher key. So these pens are lousy. If I write this, and this, it will be there, This one will motivate you to come to the board to clean the board. So I need, that is very difficult. Capital N such that for each n and m greater than n, an inverse minus am inverse less than epsilon. So this is rough work. Now I am doing an inverse minus am inverse is 1 over an minus 1 over am. This is absolute value of an minus am divided by an times am in absolute value. However, here we know, since it is bounded away from 0, however, this one has a very strong smell. Since an is bound, sorry, n going 1 to infinity is bounded away from 0. Putta, what do I know since it is bounded away from 0? What do I know? An is bounded away from 0. What do I know? You? There exists
greater than 0.
greater than 0
Such
such that mod of an
is greater than
see when there exists greater than 0 such that mod of an greater than or equal to C. For all n. class. No? Because I wrote the picture, no? Here is 0, here is minus a, here is plus a. A's are here and a's are here. Not in between. So we know that much. Then as a result, this is rough work, then less than or equal to mod of an minus mod of an divided by c square. This much is correct. No? Now what I need is, this one should be less than epsilon. This is rough work. This one should be less than epsilon. Therefore, what I need is an minus am must be less than c squared epsilon. If I choose after some capital N, an minus am less than c squared epsilon, therefore an inverse minus am inverse in absolute value will be less than epsilon. So that's how then I will say, you understand that, no? Now I will say, since an is quotient, n going 1 to infinity is quotient, when you are studying at home, don't read the book like the way I read. Because I am reading because I know this is stuff now. You always take a piece of paper and a pen. Write it roughly. See whether you can justify. Since an is quotient, there exists capital N belongs to Z plus such that mod of an minus a for each nm greater than n, o greater than or equal to, it doesn't matter, an minus am less than or equal to c squared epsilon, because c is non-zero. C is non-zero, therefore c squared is non-zero, therefore c squared epsilon is non-zero. Now I am ready to prove. They are like this. Now let, if you want jk, this n. Now let jk greater than or equal to capital N. I am going to show that aj inverse minus ak inverse less than epsilon. Then aj inverse minus ak inverse is equal to absolute value of aj minus ak divided by absolute aj ak. Then this is less than or equal to absolute aj minus ak divided by c square, we have shown. And I have chosen this capital N after capital N, no matter which n and m I choose, absolute value of n minus am less than or equal to c squared epsilon. Therefore now my j and k are greater than or equal to n. Therefore this guy less than or equal to c squared epsilon over c squared, which is equal to epsilon. Write everything. Listen. When you are working on a rough paper, you don't have to write these English words, but essential things you need to write. You need to do it at least 1 month, then you will get it. I guess you too have got it. You too are on the way to get it. But you cannot be on the way always. Thus, an inverse is quotient. Putha, you got it? Most important thing is to understand what you should do. That is the important thing. So that's why you always rough work. Even you may be thinking I am doing rough work because I am teaching. No. If I am doing this thing, I am doing rough work. How do I know what to expect? I simplify this thing, then I need the capital N like this, this is bounded, this is Cauchy. So I find the methods to handle the situation. Now this is clear, no? So this is very important. If a sequence is Cauchy and bounded away from 0, then its inverse is Cauchy. That's why we proved. Very important. I told you I will come back to the previous one that we discussed. I cannot remember what it is from this book. Where am I? So, now he says we are now ready to define reciprocation. Reciprocals of real numbers. Let x be an unzero real number. Let a and b a Cauchy sequence bounded away from 0 such that x is equal to limit. We proved that. Without proving, he cannot write like that. We proved x is an unzero real number. There is a sequence, say an, which is Cauchy and which is bounded away from 0. He proved that. Then we define reciprocal x inverse by the formula x inverse is formal limit n tends to an a n inverse. Because a n inverse is Cauchy, then formal limit, formal capital LIM n tends to infinity, whatever it is, a real number. Thus it is a real number. Now he says, we need to check one thing before we are sure this definition makes sense. What if there are two different Cauchy sequences A and B and which have x as their limit? X equals lim A and lim B, and the above definitions might conceivably use two different reciprocals, namely A and inverse B. Fortunately, this never happens. I guess that proof is not difficult. You can understand. It's a simple argument. I mean, he's saying, I should go now. Today I have some meeting in the afternoon, village meeting. Let A and B and B two Cauchy sequences bounded away from 0 such that lim n A n, lim B n, these two are bounded away, very important, they have the same limit. Two sequences are equivalent. Then lim A n inverse and lim B n inverse are the same. He is saying consider the following product P of three real numbers. P is equal to A n inverse, A n times B n inverse. If we multiply this out, you get P is equal to limit B n inverse. No, A n inverse, A n times make this one. Again he is saying, on the other hand, since limit n tends to A n is equal to limit n tends to B n, we can write P another way as first term A n inverse remains the same. Limit, he is replacing limit A n by limit B n. Then he, can you see, then last two terms cancel out. Multiply things out, we get limit A n inverse. So they are the same thing. It's a tricky proof. You understand, no? It is a tricky proof. We got it. Thus he says, now you have to be serious now. This chapter is very important. Next chapter you can real numbers. So you are very close to get to some sort of analysis. The reciprocal is well defined for each non-zero real numbers. We have exactly defined one definition of the reciprocal. X inverse not. It is clear from the definition that x inverse is x inverse x is equal to 1. He is asking why. Can you say answer for that? You have a non-zero number x. Then you have a sequence which is bounded away from 0 such that x is formal limit, capital lim by x. Then this is bounded away from 0 since x is non-zero. Then x inverse is formal limit, capital lim, A n inverse. Now that is x inverse. He is asking x inverse is equal to x inverse x is equal to 1. Why?
Formally, that's x into x inverse is equal to formally with n infinity a into a inverse. So inside the formula it's 1.
1.
Yeah.
So that then we have embedded 1 by the sequence 1 1 1 1 1. Thank you very much. This thus all the field axioms. You don't know what the field is. He is talking about field axioms. You know only petty fields, no? This sort of areas. So maybe some electromagnetic fields in physics. Thus we all the field axioms when applied to the reals are well Mukaddes service. We of course cannot give 0 reciprocal since 0 multiplied by anything gives 0 not 1. Also note that if Q is a non-zero rational and hence equal to the real number lim a Q, then the reciprocal formal limit Q is Q inverse. Thus the operation of reciprocal on real numbers is consistent with the operation of reciprocal on rational numbers. Once one has reciprocal, one can define division x over y of two real numbers x comma y provided y is non-zero by the formula xy inverse, because if y is non-zero, now we have shown that there is a Cauchy sequence of non-zero terms, no, it doesn't matter, which is bounded from 0, so we can define this thing. And just as we did with rationals, in particular we have cancellation law. If x, y, z are real numbers such that x z equals y z and z is non-zero, then by dividing by z we conclude that x is equal to y. Note that, these are clear. These are clear. We now have all 4 of the basic arithmetic operations on the reals: addition, subtraction, multiplication and division, with all the usual rules of algebra. Next we turn to the notion of order on the reals. So far what we have done is not, many things are not important in analysis, but it is justifying that what we can do, what we want to do by going through this. Here, exercises prove this and that. Third exercise is A, B, B rational number so that A is equal to B if and only formal limit of A, they are the same. This allows us to embed the rational numbers inside the real numbers in a well-defined manner, he is saying. Our next one is very important, next section. Ordering is for ordering the real numbers. Yes, we didn't come to it yet. No. He says show that formal limit of 1 over n is equal to 0. How do we prove it, by the way? Quickly. Formal limit of 1 over n is equal to 0. What do we have to prove? That means what do we have to show in order to show that formal limit of 1 over n is equal to 0?
For all epsilon greater than 0.
No, you are talking about the actual limit. He is talking about the formal limit. You have to show that the sequence 1 over n going 1 to infinity and the sequence 0 n going 1 to infinity are